Picture a gleaming new ship slipping into the water on delivery day. Now picture that exact same vessel just 5 years later, heavily degraded by the sea. The ocean is the most aggressive, corrosive environment on Earth. It's a rich electrolyte saturated with dissolved oxygen and chloride ions that attack steel with terrifying persistence, leaving heavy, weeping red rust and blistered metal in its wake. This chart breaks down the staggering financial toll. The global shipping industry spends around $7 billion every single year fighting off the ocean. That covers direct structural repairs, but also massive secondary losses from ruined fuel efficiency and emergency dry dockings. To survive this brutal arena, a massive steel leviathan relies entirely on a meticulously engineered multi-layer chemical shield. The longevity of that shield, the difference between a coating that lasts 15 years and one that peels off in 12 months, is decided before a single drop of paint is ever applied. It all comes down to mechanical adhesion. Shipyards use highly aggressive abrasive blasting, firing thousands of tons of steel grit at supersonic velocity to strip away old paint, rust, and scale. They have to achieve a strict international cleanliness standard known as SA2.5, a pristine, near-white metal finish with no visible contaminants. This microscopic cross-section shows why blasting is so important. Smooth steel offers almost nothing for paint to grab onto. Blasting creates an anchor profile, a topography of jagged peaks and valleys, usually between 50 and 100 micrometers deep, that provides a mechanical, interlocking grip for the primer. But before painting can start, inspectors strictly enforce the dew point rule. The steel surface must be at least 3 degrees Celsius warmer than the temperature at which atmospheric moisture condenses. If it isn't, microscopic condensation forms invisibly on the bare steel, blocking the primer from locking into those valleys and guaranteeing failure. Surface preparation usually accounts for only about 15% of a coating budget, but failing to achieve these microscopic tolerances is directly responsible for 80% of all premature paint failures recorded in the maritime industry. Once blasted, the pristine steel is sealed within hours using a thin zinc primer. Then comes the heavy-duty workhorse of the entire system, the anti-corrosive epoxy primer. Epoxy chemistry offers outstanding chemical resistance and blocks moisture from ever reaching the metal underneath. To boost that barrier, engineers mix in micaceous iron oxide, or MiO. As you can see in this molecular model, MiO consists of microscopic flake-shaped pigments that align parallel to the hull. They act like tiny overlapping shingles, forcing water molecules to navigate a tortuous, maze-like pathway just to reach the steel. You might assume applying more paint would offer better protection, but over-application is actually catastrophic. This cross-section shows what happens when paint goes on too thick. Volatile solvents get trapped inside the film. As they try to escape, they create massive internal stress, causing the expensive coating to crack, blister, and peel away. In marine coatings, applying more paint doesn't increase your defense. Survival requires absolute chemical precision, measured meticulously in exact micrometers of dry film thickness. While epoxy blocks electrochemistry, the hole below the waterline faces an entirely different enemy: biological fouling. This is the rapid colonization of the steel by a living ecosystem of bacterial slime, tube worms, and barnacles that lock onto the hull. This living crust acts like coarse sandpaper dragging through the water. A heavy layer of hard fouling can spike a single ship's fuel consumption by 30 to 40%, costing millions of dollars and adding tens of thousands of carbon dioxide. To fight this without using the highly toxic legacy chemicals of the past, scientists developed self-polishing copolymers. This diagram shows how the polymer binder reacts with seawater to slowly dissolve. As it washes away, it continuously exposes a fresh layer of highly regulated biocides underneath, renewing the whole surface. For fast-moving ships, there's a biocide-free alternative: foul-release coatings. Instead of actively targeting the organisms, these silicone hydrogels create an ultra-slick, non-stick surface. The organisms simply can't maintain their mechanical grip, and the friction of the moving water shears them right off. It is estimated that universal adoption of advanced anti-fouling across the world fleet could save up to 75 million tons of bunker fuel every year. That translates into a reduction in carbon emissions measured in hundreds of millions of tons, a massive environmental dividend applied directly to the hull. Even the best paint system will take a beating from anchor chains, tugboats, and floating ice. Every scratch that exposes bare steel immediately becomes a highly active, localized corrosion cell. To defend these inevitable scars, naval architects deploy an electrochemical backup, cathodic protection. By bolting highly active metals to the hull, they artificially polarize the ship. As the schematic shows, a zinc anode will continuously dissolve its own electrons into the seawater electrolyte, so the surrounding steel remains completely intact. On massive container ships and military vessels, engineers upgrade this to an active electronic system. Instead of heavy zinc blocks, a dedicated power supply drives protective direct current out through permanent titanium anodes, flush-mounted into the hull. But a failsafe doesn't replace the need for an absolutely perfect initial coating. Inspectors hunt for microscopic flaws using high-voltage holiday detection. They sweep an electrified wand carrying thousands of volts directly over the dry paint. If there is a microscopic pinhole, an invisible defect, the high voltage arcs to the bare steel with a visible spark and a loud crack. These obsessive inspections are mandated by international maritime law under the Performance Standard for Protective Coatings, ensuring the most vulnerable tanks on a ship guarantee at least 15 years of useful life. By the time this phase concludes, the vessel is defended by a unified triad: impassable chemical barriers, active electrical polarization, and microscopic auditory inspection. Back on the exterior, the ship receives her final layers. Right at the waterline is the boot topping stripe. This narrow band faces a brutal microclimate of continuous UV radiation, cyclic seawater immersion, and mechanical abrasion from tugboats, demanding a highly specialized, ultra-durable hybrid coating. Above that sits a high-gloss, UV-resistant polyurethane finish. This is the top coat that gives the towering superstructure its owner's chosen colors. Designed to withstand intense tropical sun and freezing polar winds alike. The transformation is complete. What began as a vulnerable, hollow steel shell is now a fully sealed, biologically defended, and electrically charged marine leviathan. The deafening noise of the shipyard finally fades. The massive dry dock valves are cranked open, and the cold, dark ocean rushes in, flooding the concrete floor and embracing the newly painted hull for the very first time. This millimeter-thick barrier is all that prevents the ocean from reclaiming the steel. With her armor in place, the vessel is ready for her true element, setting the stage for the official launch and sea trials in our final episode.